Hey everyone, welcome to the Massive Algebra live stream. I'm your host Peter, and basically we are going to get into it today with coordinate systems, vectors, and hopefully a little bit of tensors for today. Anyway, I am going to be joined with one of my friends from the Discord server, Sascha, so I will bring him in because we're both on Discord, so just give me a quick second here. Hey Sascha.
Hey, how are you, Peter?
I'm alright, how are you? So you're on stream right now, so if you want to say hello to everybody in the chat, you can.
Hi everybody.
So basically like yesterday, if you weren't there last stream, Sascha was willing to offer his knowledge, more of his knowledge, because he gave us a lot of knowledge yesterday, about mainly, I think it was like surrounding the relationship between multivariable calculus and linear algebra. Is that correct,
yeah.
Sascha? Okay, so hopefully we'll learn more about, I guess, different coordinate systems, basis vectors, as well as maybe a little bit about tensors here and there. So we'll try to get through as much as we can during the time. So yeah, so Sascha, the floor is all yours.
All right. So first, I want to go back to the basic and talk about differential function.
Okay.
Oh, that's too thick. Yeah. Make my stroke a little bit thinner.
Just go up a little bit.
So So what I want to talk about is differentiability in multiple with function with multiple variables.
Okay.
Okay, so we're all familiar with differentiability with one variable, but we would like to extend this notion to more variable.
And also, guys, in chat, if you have any questions, like you could just type it into the chat, and I will relay them back to Sascha if you have any questions. So feel free to type in whatever you need to in the chat, and we'll try to get back to it as soon as we can.
Okay, so usually differentiable function for one variable is something like that. You have like, I will probably not spell out all the details, and sometimes we will maybe hand wave a little bit because
right.
The idea is kind of get you the idea and how this applied to computation and how this is related to tensor. But so we are gonna assume f is some function defined on some open set of the real that takes value in the real number. So if you don't like the word open, you can replace it by a small open disk, open ball if you prefer. I mean, in that case, there would be some just open interval, okay?
And this is in like two-dimensional space for the small open disk?
Yeah, but here we're just in one dimension, so the small open disk is just an interval.
Oh, okay, so it's one-dimensional, okay. Gotcha.
So yeah, if we draw the picture, F will be something that map... so U will be something like that, like this is an open interval.
Oh, okay. Right.
And this will be mapped to the real line.
Alright.
By the way, I wrote my my open interval with those brackets.
Yeah. It's
anyway,
actually.
I guess you prefer to use parentheses, so.
No, I think the bracket. I think it depends. Like, is it supposed to be an open interval or a closed interval? Because I think we use those brackets for closed intervals, and I think like the way you wrote it, we do it the opposite way. So basically, I think like the inside of the brackets point inside. Well, yeah. Like while yours are outside. So I think that's what you grew up with, right? Like they're pointing that way. Okay.
Yes, so if they're pointing inside, for me it means that it's a closed interval, and if they're pointing backward, it means it's a
interval. Really? So basically you just write the same brackets, it's just the opposite way, right?
Yeah.
Oh, okay.
So in English you would probably write something like that. I mean.
Yeah.
And so what does it mean for a function to be differentiable? So let's say f is differentiable.
If you guys don't remember the definition of what differentiable means, it's basically one, it's continuous. So think of it as like you can write the curve without taking your pen off the paper. That's the simplest way of defining it in a short amount of time.
So f is differentiable if you have the following quotient, right?
Yep, the definition of a limit. We all know where that's from. If you haven't caught up with calculus, you will eventually learn it.
And the idea of a function being differentiable is that, okay, let's maybe just graph the graph of such a function. It would look something like that. I don't know, maybe I can draw a parabola or something. And maybe this is our point x0. The idea is that at the points x0, we can approximate the behavior of the function by some line, the tangent line. And what is this quantity representing? Is representing the slope.
And I'm pretty sure all of you guys are so used to slope from algebra, if you've taken algebra before.
Okay. And now the question is, how do we extend in higher dimension? So maybe we can try to find some feature of this definition. So the definition is so if we look back at the function the graph I wrote below, one of the key aspects is that a differentiable function, the behavior of the function should be can be studied with some linear function. Okay, so example, in one variable we can use this blue line to study, for example, slope, and slope tell us about how the function grow and so on. Okay, so what's going on with the multivariable analog of this? So differentiability. In higher dimension. Okay, so again, we're gonna have pretty much the same setup. So we're gonna have some open disk. This time it will be probably a somewhat more reasonable disk, sitting inside of some Rn. So this is just an unfold copy of R. For example, again, R3 or R2, and and this is mapped to Rm. Okay. And now I will write a definition, and maybe the definition will feel a little bit strange at first.
Yeah.
But we're gonna check it. It's kind of reasonable because we're gonna show, for example, that it gives us the case we already know about one variable. Okay.
Yeah.
So f is let's again take a point x0 inside of U. So f is differentiable at x0 if, and now maybe this is gonna be weird, okay?
Okay.
Because here, if we think about it, what does the slope tell us? It tells us about how the function grow, right? But the thing is, in y dimension, you only have one direction. You can only move along the x-axis, right?
Right.
But in higher dimension, you have multiple direction that you may consider.
Yeah.
So the differential cannot be a number because it should be something that take a direction and give you maybe some vector or some number. So let me just write the definition, and after that we'll try to make sense of that with an example.
Wouldn't it be like I'm trying to I guess hypotheticalize what you're trying to mention? It's like, wouldn't it be possible because the one with lower dimensions we have a line, right? So yeah. If we were thinking slope, for example, but it's in higher dimensions, wouldn't it be possible to basically say a plane in that case?
Yeah, but the problem is in the plane you don't you don't really have a notion of a slope, because depending on which direction you go in the plane, your function is gonna go differently.
Right. Yeah.
So slope is a little bit more complicated. And hopefully I will try to...
But that's getting close to a primary idea, right? So it's we have a line that basically tells, for a curve, we have a straight line to basically give us the tangent of the slope of that particular point on the curve. So for higher dimensions, right, I guess a plane would be considered I guess almost equivalent to the line in the two-dimensional context.
Yeah. Pretty much. Okay, so f is a differential function, and what it means to be differential at x0, it means if there exists a linear map.
Okay.
So maybe this is the new data that we seems to not have in the one-dimensional case, but I will show after that indeed we already had. It's just the one-dimensional case, everything is somewhat trivial. So let's maybe call it L, because I don't know, linear map being called L is kind of a nice name to give.
And L is supposed to represent, I guess, the linear transformation?
Yeah.
Okay.
So if we pick, for example, coordinate on Rn, the linear coordinate, for example, if we take the canonical basis, then it will become a matrix.
Okay.
And after that, we're gonna see what this matrix looks like, because I mean, this might sound new to you, but at the end you'll see that you already knew a lot about it.
I think it was familiar with the Rn to Rm, so I was like, wait, I've seen that in linear algebra.
Okay, so we must have some linear map from Rn to Rm, and then we need some conditions. So what's the condition? The condition is if I take okay, maybe I will just change a little bit my notation. Instead of writing x, because maybe you can confuse that with the x-axis in, for example, R2, I will just write p, just to make sure that I'm talking about the points.
Hey,
that Academy. On the x-axis.
How are you doing? I'll give you a shout out, Academy. Keep going, Sascha. I'm just gonna give Academy of Useless Ideas a shout out. If you guys are not familiar with Useless Ideas, well, I mean Academy of Useless Ideas, they are also an awesome math streamer and very, very knowledgeable about what they talk about in each of their streams, so check them out. Yeah, so Academy, we're going over basically like the relationship between multivariable calculus and linear algebra. So hopefully you can enjoy Sascha's like ultimate instruction. No, it's okay. It's okay. It's more like for all of us. It's more like consider it like a research seminar. Wouldn't you say so, Sascha?
Oh. Yeah, I did some typo. I'm sorry.
Oh, you're rewriting the notation, right? For P, right?
Yeah.
Yeah, it's fine. It's
okay. I want it to be P. Okay, so the function is said to be differentiable if we have the following limit that exists.
Okay.
Okay. So maybe we should first ask: is this definition reasonable?
Okay, so that'll be the first question for not only me, but also chat too.
Well, I cannot write, I guess.
That's fine.
So maybe, I mean, if the definition is supposed to be a generalization of the one-dimensional case, we should be able to get back the usual definition. Mm-hmm. So if it's differentiable in the sense that we all know from calculus 1, it should be differentiable in that sense also. Okay, so maybe I can show you. Maybe I can show you one direction, so I can maybe show a different. So maybe I will just give it those name.
Okay.
Maybe I can call this 1 the first definition, and 2 the second definition, and I want to show that 1 implies 2.
Okay.
I mean, yeah. Mm-hmm. I will not give a very rigorous proof, but I will just give you some idea why it's true. I mean, this one I can probably write everything down.
Okay.
Okay, so first of all, we have. So the first definition says we have the following. Right?
Right.
One way that I can okay, so this will be equal to some constant, right?
Mm-hmm.
Let's maybe call it A. So this is the differential of f at the point x0. Let's call the derivative A. So
okay.
Just a number.
Mm-hmm.
And okay, what I can do is I can rewrite this limit. I can say, well, if I want, I can just move the A on the left side, because it's just a constant. Right?
Mm-hmm.
And then what I will get is that this is equal to 0. But this is exactly the same thing as saying that the absolute value of that is equal to 0.
Okay.
There's no like loss of information putting the absolute value here.
So where did the absolute values come from again?
This is just the fact if you have, for example, limit of something. I don't know, maybe we can call it f of x, right?
Mm-hmm.
It's equal to, I don't know, b. I mean, maybe you can say 0 to be exactly in the case we are.
Mm-hmm.
This implied that the absolute value of this will also equal 0.
Okay. I just came up with I guess a connecting thought in my head, but you can tell me if it's wrong. Is the absolute values there because the limit, if the limit exists, it's applied to both sides? Like, you know how you do the absolute value and basically you take the distance from both the negative and the positive direction?
Not really. I mean, yeah. I mean, the reason why I put absolute value, so I could have removed the absolute value, but the reason I want to have absolute value is because Absolute value are actually the analog. I mean, they're the norm in the one-dimensional case. That's why I'm putting absolute value. But the only important thing is, if I have this limit above, well, I mean, maybe I can use the thing I wrote on.
Oh, okay.
Right
I thought you put the absolute value in there because, like, you know, the limit has to exist, and the only way it has to exist is that if the limit is the same for the left side and the right side of the limit. That's why I asked that.
Yeah, that's not really related. I mean, the reason I can write that is because absolute value is continuous, so I can enter a limit inside of it.
Okay.
So,
carry on.
Okay, and so now here we can just do some rearrangement. So what I would like to do is put these a's on the same denominator, so I could do something like that. So I will get something that looks like that. Okay.
Okay.
And now what I choose as my L. So if if we define this as follows. If we define our linear to be just a times x,
Okay.
then this whole expression can be written as minus L of x minus x0. Alright. And here I want to stress something important, is this is linear.
Okay.
And now maybe I can just maybe I can just clean up a bit the absolute value. So of course the absolute value can distribute over the numerator and over the denominator, so we get something like that. And that's exactly the second definition, right?
So for like single variable calculus, right?
Yeah.
When you say that, no, I was gonna ask a silly question, but like, because you said that one is linear, right? So
yeah.
When we're doing single variable calculus, when we're actually doing the derivative, since that limit is kind of like the definition of a derivative, wouldn't you say that the operation that we're doing is, I guess, linear in some cases, or is that the wrong way to view it?
So what's going on in the one-dimensional case is we are computing this quotient, right? But at the end we get some a, and we say this is some slope, right? Well, this a is exactly the slope of the linear map I get below, right?
At that specific point, right?
Yeah, at that specific point, yeah.
Okay,
Maybe,
okay.
yeah, for x0, yeah.
So
if I vary my x0, then I will get some...
So the reason why it's linear is because basically at specific point, that would be considered like, I guess, a linear slope, right? But if you take the whole derivative, it's just a function where it's like, you know, it can go to the curve and like you get a straight line here, but you get another straight line there, that's a different slope,
exactly,
right?
yeah, that's
Okay, gotcha.
So we get the same thing. And as you can see, the reason why we're able in the... So if we go back just to the second definition says a function is differentiable if we can approximate by linear function, right? I mean, that's like the big shot of it. Right. And in the one-dimensional case, kind of weird. We're just like computing some quotient and we're getting some number. So it's a bit weird that the general definition say the derivative should be some function, some linear function, and the one-dimensional case is just a number. And the reason why you're able to just to make everything work with just a number is because linear map from R to R. So if I have a linear map from R to R, then there is not many things that can happen.
And that's just R to R, like basically just the real numbers upon the real numbers, right? Okay.
Yeah, so if this map is linear, the only way you can have something like that is you have you just take x and you send it to a multiple of x.
Mm-hmm.
And that's the reason why in the one-dimensional case we just get a number, is because linear map from R to R are completely determined by the value of this constant.
So does that have anything related to like a vector space where they emphasize a lot when it comes to vector addition? It has to be a vector in addition to like scalar multiplication, where if it's multiplied by... Okay.
So when I say it's linear, I mean it's satisfied that Lx plus y is sent to Lx plus Ly. And the same is true also for multiplication. So if I have a times x, it's become a times L of x.
Okay.
Okay.
All right.
And that's the same definition in the higher dimension. Okay.
All right.
So okay. So we kind of check that at least our basic definition implies the second one, and I mean it's basically the same step. We can also show that if a function is differentiable with respect to the second definition, then it also has to be differentiable with respect to the first definition.
Mm-hmm.
Okay, so we kind of see that at least we get back the one-dimensional case.
All right.
So we at least have something that generalizes. But I mean, so far we haven't done anything very interesting because we just state facts that we already know, but just in a different way.
I mean, I find it interesting, but like, I don't know, chat. Chat, you could basically say if you don't find it interesting. Carry on, Sascha. I'm sorry.
Okay, I will go back just to some part of the notation I use, okay?
Okay.
So maybe I will just go back to the definition. I will just stretch something because you said something important in the one-dimensional case. You said, oh, the line you get depends on the point you choose, right?
Right.
So I'm gonna just stretch it in my definition too. I will just maybe add some P0 here.
Okay.
Okay, just under the L, just to state that this is like the best linear approximation if you want at the point P0.
Mm-hmm.
But usually we don't use this notation. We don't usually write the L. We have a better notation for that.
Okay.
So if, again, same setup. So we have use some open set from Rn to Rm. If if f is differentiable at let's say x0, then we write if I want to use the notation I used previously, I should just put the P0. Then we write df of P0. Okay. So usually we use this notation, and this is called the differentiable. The different. F at P0.
So what does the L represent?
So the L is just the L from above. So maybe I can just spit it out all the definitions. So it's something like that.
Oh, like L to R and to R, right? That L, right?
Yeah. So that's the linear map.
Okay.
So maybe if I rewrite everything that we wrote before, it would be.
So the thing you were alluding to yesterday was this, basically, the differentiable of a function at a certain point is like equivalent to, say, the linear transform of that onto P, right?
Yeah. So we get something like that, and yeah. So just as a reminder, df is again a linear map from Rn to Rm.
All right.
Okay.
Okay.
And now maybe we're gonna so usually when you do an analysis class or a calculus class, usually you will develop a method for finding if a function is differentiable or not. Okay.
Mm-hmm.
But because the definition is kind of hard to check usually. Usually there's like a nicer thing that you can check that ensure that your function is differentiable. But at least we're gonna just build the intuition for one specific case that I want to understand.
Mm-hmm.
Is the case of f is some function from R2 that takes value inside of R. Okay. So for example, an example of such a function would be f that take x and y in the xy plane and send it to x squared plus y squared. Okay.
Mm-hmm.
So maybe we can just draw a picture of this map. I mean, just in general, so it's going to be something like that, right?
Mm-hmm.
So we have the plane here, and we map to a line. So let's pick a point P0. Okay. So also we're gonna assume that this is differentiable at P0. So P0 is just a point inside of U as usual. Okay, and now I told you something very important about the one-dimensional case, which is different in the higher dimension. In the one-dimensional case, we have only one direction. We can only move along the x-axis, right? We can either go to the positive or negative, but I mean, if the function is differentiable, it does not change much going to the positive and negative side. So what we're gonna do now is, so here we have a lot of direction, right?
Right.
For example, we can go to the horizontal direction, we can go to the vertical direction, but we can also go to some mixed state, right?
Right.
There's like infinite dimension we can go around, right?
Yeah.
It's pretty much like every angle of a circle like is a direction for that. So okay, I will just fix some notation. So let E of x, with a lower x like that, be the standard vector 1, 0.
Okay.
And be E of y 0, 1. So you probably call them I and j or something like that.
Right.
Okay. And what I would like to do I would like to compute I would like to compute the differential at those vectors. Okay, so ex and ey. Okay. Just to be sure we're talking the same thing. So here we're mapping some open set of R2 to R. So the differentiable at some point will be a map that goes from R2 to R. So the way you have to think is it takes some vector and spit you some number, right?
Okay.
So in that case, we're really interested in what happens if we give it ex or ey.
Okay.
Okay. So
this
the standard.
So this is the linear transformation because it's taking from like a higher dimension into a lower dimension space. Correct?
Yeah.
Okay.
So what we're gonna do is we're gonna so here I said that so if we go back to the definition of the differentiable, we have a limit, and this limit is so it basically tells you that for if you make p close enough to p0, you must have the following equality hold, right? But I mean, if you think about it, p can approach p0 in like a lot of direction, right? Like we really established this with the drawing below. But here, what I want to do is just approach it from only the x-axis or only the y-axis. Okay. So let's have a look at that. So let's consider the path so what would be something like that. Okay, so maybe I can just draw it in the plane. So here we have p0, and then here we have the x direction, right? Along those lines. And what I want to do is look. So this is, I mean, the line I wrote in red is pretty much parameterized by this equation, right? Like if I vary t, I will just get a point on that. And what I want to do is study when t get close to 0.
Okay.
So I mean, in the definition of I have a differentiability. The limit is just a point getting close to p0, so every direction should work. Here I will just I will try to just compute it along one direction to see what I get.
And this is when you basically like the derivative rules in multivariable calculus is that, like, if you want to I guess like compute the rate of change like in one axis but without altering the other, this is when you actually like treat the other variables as constants, correct?
Exactly, yeah.
Okay.
So exactly, we're just varying along the x-axis. We are not varying along the y-axis.
Okay.
So maybe you can. So you already get some good insight. You say, okay, this guy is basically measuring. I mean, the differential is basically measuring the variation of the function, right? But as we are in the like two-dimensional case, we have like a lot of direction that we can measure the variation, right?
Right.
And the idea here is we're gonna measure the variation along the x-axis, and this will and for y we're gonna measure the variation along the y-axis, right? So you probably have something already that you know about that. Like you probably know just like something from calculus that you've already seen that do that exactly. Do you have an idea?
So what was the question?
So what do you think I will get when I will compute this thing?
If you compute that in relation to the x-axis?
Yeah, so I'm measuring the variation of my function along the x-axis.
Okay.
What do you think I will get? You already have some like tool from calculus that does that.
I mean, like practically, like you would have to integrate all. I mean, not integrate, differentiate all the functions involving x at that point. So basically, like the x-axis, or at least like the point on the x-axis, you're getting closer and closer to it on the x-axis. But it's not affecting anything on, like, say, the y-axis.
Yeah, but you have a name for that.
Name?
Yeah, this is called
partial derivative.
Partial derivative. Yeah.
Yeah.
So this guy should, I mean, intuitively, when we're gonna do this computation, we should find that this guy is the partial derivative of f along the x-axis,
right,
at point p0. This is what we should get. So let's see that we indeed get that.
Okay.
So now my limit from above, if I consider this path, will be when t goes to 0 of the p0 P0. Here I have to write everything minus the point, so I will get minus P0. But I don't get lost in writing everything out. And below we're gonna have P0 plus T times Ex minus P0. Okay.
So
So
what does T represent in this case?
Just us moving along the path I choose.
Oh, okay. So
T just basically mean we're moving around the x-axis.
So T is like kind of like a scalar in this case.
Yeah, exactly.
Okay.
So as I said, so we know this is equal to 0 because this is a special case of the limit above. We just consider one direction.
Uh-huh.
So we know this is 0.
Okay.
Okay, so maybe now we do some cleanup. So we get that. Below, so we get the P0 are cancelling out.
Mm-hmm.
So we basically left with T times Ex, right?
Mm-hmm.
But that's a scalar, so I can put it out of the absolute value, out of the norm. We just get absolute value, and norm of Ex is just 1, right?
Mm-hmm.
So the delimiter just becomes absolute value of T.
Okay.
And now on the right side, so similar thing happened. I get so I have P0 and minus P0, so they cancel out. Here I have a T, but this function is linear, so I can get the T out.
Mm-hmm.
So I will get minus T df P0 E of X. And of course everybody, oops, that's what I meant. How do I undo? And everybody is on the absolute value of X. Okay, something like that.
Mm-hmm.
So I just do some cleanup. Now we can split the sum in 2. And maybe I can just put the absolute value on the whole expression, so we get something like that. T plus T times E of X. T minus F P0. So here we'll have the T and the... So we'll have the T that cancel out, so I just get minus df P0 E of X. And absolute value. Okay.
Mm-hmm.
And now what's important is that guy on the left.
Yeah.
When I take the limits, this is exactly... sorry, I use small f and big F. I shouldn't have... Yeah, sorry.
Sure.
So my bad, I did some typo.
And also in chat, if Sascha asks a question to me, you guys are more than happy to give your own answers as well in the chat. This is sort of like our own not for an exam, but basically just our own little mind space, so that we can actually see where we can actually pull this information from. So it's a creative way of actually looking at the math.
So this guy is exactly by definition the partial derivative of f with respect to x at the point P0.
Okay.
So what we conclude here is that evaluating our differentiable at P0 along the x direction just give you back the usual partial derivative. And I mean, you can probably trust me on that, but you can also just do the computation again. But I mean, we're just gonna replace the x symbol by y, so
Okay.
we're not gonna do that. But you can also check as well that these will compute the partial derivative of f with respect to y at p0. So we get that. And now we get a pretty good description of df, right?
So the ex and the ey, right? Are those the basis vectors of?
Yeah.
Okay.
So I said before that ex was 1, 0, and ey was 0, 1.
So they're not only basis vectors, but they're also unit vectors.
Yeah. I mean,
Okay.
yeah. Here you can see that.
Okay.
So, well, I actually use it in the proof, right? Because I said, like, when I was at, where I used it, here. From going from here to there, I used the fact that the norm of e of x was 1. If, for example, we would have, instead of making e of x a unit vector, we would have say, okay, I want to take twice e of x. Then I would have in my numerator a 2, right? 2 times t. But as dff is already linear, we already know that's the same thing as computing twice the... I mean, not twice, but 2 times the partial derivative.
Okay.
So recall, d of f is a linear map from R2 to R. Okay?
Right.
And what we just did is we did a computation with basis, right? Because as you said, e of x and e of y are basis. And if we have a linear map and we know that its value on the basis, we know everything about it. Okay, so this is just a thing from linear algebra. So if you have any linear map and you know its value on the basis, you know everything. And usually what this leads us in linear algebra, it leads us to a computation with matrices, right? So if we want to write this linear map as a matrix, in the basis, in our standard basis, so ex and ey, and the basis on R is just the number 1, so we don't get much. We get the following matrix. So it's a map from R2 to R, so we expect to have a matrix of this form. Some row matrix. Okay. And this you sort of know what it is, right?
I mean, like, besides being the partial derivatives of each axis, and but for some reason my mind is also going to the Jacobian.
Exactly, that's really good.
Okay.
That's the Jacobian.
And that's all. Is that in R1 or is that in R2?
So this is for R2.
Okay.
So we have a row vector. So it will take some column vector and gonna spit some number. Maybe we can do some computation after that with.
Yeah, because I remember when it's like when it came to covariant and contravariant components. Like I think like you can think of them as row and column vectors. So I think like the question I have in my head is that how do you know which map maps onto a row vector and which map goes onto a column vector?
So I mean, this is just a matrix, right? So
Right.
the GIF I wrote below is just the matrix you get if you look at the map from R2 to R, right?
Mm-hmm.
You will get you will always get a row vector like that.
But why is that though? Because like, how do you know it's not a column vector with the same components?
Well, okay, so so this is basically a question from linear algebra, but so okay, so I will just maybe write you down some. So how does the matrix linear map work in general?
Yeah.
So if you have L,
Mm-hmm.
yeah, go on.
Oh no, I was about to say like, if it's like an explanation that's too long to explain, you can basically tell me, oh, look this up, like, you know, like on your own time.
Oh, no, I
Like,
I think that's important, so I will just maybe take the time to.
No, I mean, I'm just saying, like, you know, for future reference, because you know I researched this like off stream too, so you know, I will do my homework.
So if you have a map from, let's say, Rn to Rm, but it also works for any vector space.
Mm-hmm.
And let's say we have a basis, okay? Maybe
Okay.
we have E1 to En is a basis of Rn, not necessarily the standard one.
Mm-hmm.
It can be any basis. So you know a basis just means that you can write every vector of Rn as a unique linear combination of those guys.
Right, right.
And you can do the same thing. You can pick a basis on Rm.
Mm-hmm. Because like when we think of a basis, if we're trying to make it like, I guess, more visually appealing for people to understand, it's like, it's basically the way that space is sort of like shaped in order to give you the coordinates that are in that space, right? Is that's a good way to phrase it, right? So that people like that are not like, I guess, mathematically abstractly that can think abstractly would think of it, right?
Yeah. And what's nice about that is if we know. So for example, if you take an element of our basis,
Mm-hmm.
let's call it LE. So it will be something that live in Rm, right?
Mm-hmm.
So it would be some linear combination of those guys, right?
Mm-hmm.
And I will probably get the I will probably get the indices wrong, but
No, that's okay.
I think it's something like that.
If anyone in chat knows, like, if sees any like errors that both of us make on our part, more likely it will be me. But if you see any errors that are done in any of our parts, like, let us know.
So let's see. So it's supposed to be I. So I is tell you the row you're on.
Mm-hmm.
Oh, it should be. I think this. I wrote it backward. Okay, maybe let's just change that for a J and change this guy for an I.
Yeah.
So you will get some coefficient here, right?
Mm-hmm.
Okay, maybe I will just write down, then I will see if I write the question right. So you will get a matrix with if you take those coefficients. Let's maybe call it A. Where the entries are Aij, right?
Mm-hmm.
And the idea is A will have the following form. So the first column, this guy will be a vector L of A1. The second column will be L over 2 and so on.
Okay.
Here there's kind of a nuance I have to say. So those are column. When I say that we wrote L of E1 in the column form, I mean we wrote it using the BJ basis.
Okay.
So if we go back to so if we go back to our example from R2 to R.
Mm-hmm. Yeah, it's going well, Fanbox fan. What's the best part of your day so far?
So we have g of f, which is which map. I mean, it's probably just the f I should write.
Mm-hmm.
F of p0 does go from R2 to R. And we have pick the basis, the standard basis, so e of x and e of y on R2. And we pick the trivial basis on R, so we take one as a basis on R. I just want to state it, but yeah. So what we have is so what we compute before is we compute that the differential of p evaluate to e of x or e of y, doesn't matter. It's just the partial derivative. So we can write is as do you still have the screen?
Yeah, I still have it.
Okay, yeah, mine just flipper.
Okay. What'd you type, FemFuxFem? I just substitute and taught a calculus lecture on quotient and product rule for a friend. That was fun. Nice. Okay, thank you for the lurk, FemFuxFem.
I'm not sure where.
Yeah, go.
Oh, sorry.
No, I was gonna say to chat. Yeah, guys, like you can still chat in the chat. Like, don't feel like you're interrupting us. Like, we're gonna like look at what you type up, and then basically like like I will respond to it as much as I can, and plus like maybe like you guys will give us ideas about like what we can add to the, because this is not really more like a study session. It's more like I guess you can consider it like a I guess a colleague to colleague lecture in a way. Of course, like Sascha's just teaching me, but don't feel like you're interrupting. You guys are good.
I don't have the screen anymore.
Oh, you don't have the screen anymore? Do you want to re-click the link, or do you need me to resend the link, or what?
Can you resend the link?
Sure. Let me okay, copy that. Okay, paste. Alright, try it now.
Yeah, okay. Maybe I can open it in incognito. Yeah, is this I only have like a new canvas. I don't know why. But okay, let me see if I
can you write in it or no?
Yeah, I can write in it, but it's like empty.
That's weird. Did you click the actual link, or did you click on the image?
No, I click on the link.
Okay. Because I remember I did that the last time, and I realized it was blank.
Do you see the scribble I wrote?
No, I don't see it.
Oh, okay. I think we should probably just create a new link or something.
Okay, you can create it.
Yeah, that's a bit unfortunate.
I mean, I still have the old notes, so like we can, if you need me to reference it back, I can put it up on stream for all of us to see.
Yeah. Share, start a session, copy link. All right, there you go.
Okay, click this one. Yeah, we still have the old one. Okay.
Okay, so what I was about to say, boy, this is what I want. And of course, I have to do the thickness part. Okay, so as I said before, we have this that map R2 to R, and we took the basis. X, E, Y, 2 and 1 for R. And the thing we showed previously is that when I compute the differentiable at those basis vector, I just get back the partial derivative, right?
Mm-hmm.
And here I'm just going to be a little bit more careful. I'm going to just we get the partial derivative times 1. I mean, that does not change anything, but it just would be important for oops, here should be no 0. The same go here, right?
Mm-hmm.
And now if we so this is a linear map, so we can do the usual thing we do with when we have a basis in a linear map. We can write the associated matrix. Here, as you said before, this is just the Jacobian matrix.
Mm-hmm.
And so this is a map from R2 to R. So the column of this matrix will be the image of my basis.
Mm-hmm.
Okay.
Okay.
But they will be written down in the basis of my of the space where I'm going to. So I'm going to R, right?
Uh-huh.
In R, there is only one basis. I mean, there is one vector. This is just a vector 1, right?
Mm-hmm.
So my column will be we only have one component, so they will just be a df dxp, and I will just have my my partial derivative like that.
Okay.
So maybe we can do a bit a more interesting example. So let's say F is a map from some open set of R2 to R2, okay?
Okay.
And it's differentiable, I mean, as usual. So the differentiable will now be a linear map from R2 to R2, right?
Okay.
And here what you will get is that, so first of all, if you want, you can see F as a two function that takes value inside of R.
Mm-hmm.
I mean, I don't know if you have ever seen that, but maybe I can just write it down. So you can see it as that f1 of xy and f2 of xy. Okay.
Is that like the function like within its own vector space?
So f1 is just a function. So
Mm-hmm.
the fi are just functions that go from U to R2 to R. So they're just like component. There's like just component for f.
Okay.
Because f take value inside of take value in R2.
Mm-hmm.
So the Jacobian of f in that case. So if we take, for example, standard basis in both cases,
Yeah.
the Jacobian of f will be. So now it's a map from R2 to R2, right?
Right.
So what we'll get as a matrix, we'll get a 2x2 matrix, right?
Mm-hmm.
And what will be this matrix? So, so the first column will be the image of looking at the variation of x along the x-axis, right?
Right.
So this is basically just the same thing as taking the differentiable of the first component with respect to the x-axis and taking after that the differentiable along, I mean for f2, but also along the x-axis.
Mm-hmm.
And the second column will be the same thing, but in that case we're gonna study the variation of y, so we're just gonna get that.
So wait, is f in this case, is it a vector value function?
Yeah, so it goes from R2 to R2.
Okay.
And this is like a good example because we can see a first coordinate using that.
Okay.
Okay. And now I said there is a very important slogan in multivariable calculus is you want to reduce problem of analysis to problem of linear algebra.
Right. Yeah, I remember that one.
Okay, that's like a very important motto to remember.
Okay.
So here I'm gonna state a theorem. It's called the inverse function theorem. Okay, I'm not gonna put all the hypotheses because I don't want to go over the roof.
That's fine. I'll probably look it up like afterwards.
I mean, I can put the hypothesis and just not say much about it.
Mm-hmm.
This F is a map from Rn to Rn.
Mm-hmm.
U is also an open set, and F. Okay, I mean this is like a technical condition. We have to assume that F is of C1 regularity. So C1 regularity means that all the partial derivative are continuous.
Okay.
Okay. Usually you can strengthen that. Like, for example, if you know that f is out of C2, you will get a different conclusion. But
So what is C in this case?
so C1 is just like a regularity. So C1 just means that all partial derivatives are continuous.
Okay. Is it like C1 is like C1 onto C, right? Is that what you've written over there?
Yeah. Donc, so this is C1 on U.
Oh, and U. Okay. Okay.
So U is a function that probably
It's a
the more
subset
correct,
of. It's a subset of R, which is basically what we're working with.
Yeah.
Okay.
probably the a better way of writing that is something like that.
A conventional
So all
way of writing
partial-
is that. That's what
Yeah.
you mean, right? Okay.
All partial derivatives are continuous.
Okay.
For example, there's like other regularities. So for example, if you have C2, it means that you know that all partial derivative. You know that all second derivative exist,
Mm-hmm.
and they're also continuous.
Okay.
When I say second derivative, par contre, you have to be a little bit careful because in the one, so you don't just have that taking two partial derivatives to x is continuous and two partial derivatives to y is continuous. You also have like the cross term.
Like the cross ones, like basically
Yeah,
X to
the
Y
X to Y.
and Y to X. Yeah, I remember that.
Yeah.
I think with partial derivatives, like because before I think like with each like it would be like two, like it would be like I think like two. No, not two. When you take the derivative, it's basically just one way of taking it. But then when you do it from like multivariable, you have to do it multiple ways because it's sort of like a plane instead of a line.
Yeah. So yeah, you have to check a little bit more.
Mm-hmm.
Maybe I can explain. This is not like the best definition. Like checking all the derivatives is not very a good definition because the problem with partial derivatives is it depends on which basis you choose, right? Because here what you said, what we found is that the Jacobian is basically the differentiable. At one condition, we have to pick a basis for a vector space. So if our definition of C1 is all partial derivatives are continuous, we kind of get into a silly problem that okay, if I change my basis, so I get different partial derivative, will those also be continuous? So I have that's kind of an annoying definition. There's like a better definition of that, but I don't really want to get into that because I want to.
I'll definitely if you guys want to in the chat, you guys can look it up, and I'll definitely do my due diligence to look it up. So it's like the inverse function theorem, right?
Yeah. So probably during the summer, if you want, we can go a lot more detail about the linear algebra and the calculus and analysis of that. But
absolutely. Yeah, we can.
Right now, I just want to give you some intuition.
The broad strokes, yeah.
Yeah. So assume there is some point P0 inside of U, such that the differentiable of P0 is invertible.
Okay, and what are we defining as invertible in this case?
So just recall. So this is a map from Rn to Rn. So this is a map for. So the differential will be some linear map from Rn to Rn.
Mm-hmm.
And we want this map to be invertible. So it means that there will exist some inverse function. Let's call it like that.
Mm-hmm.
Such that when you compose those two functions, you get the identity.
Oh, I think I read this morning concerning basis vector transformations. Like the question is that how is if you were to change a vector from an old coordinate system to a new coordinate system, you have a transformation matrix, and then when you do the same thing with the basis vectors, it's the same method. And the question was in the book that I was reading, basically, how are these things related? And when you multiply the inverse with the actual transformation matrix, you get the identity matrix.
Yeah. So another way of saying this condition is saying that this map is a bijection. So this map is into and onto. So if you have 2 points which are mapped to the same value inside of Rn, then those 2 points has to be equal. This is the condition to be into.
So when you say bijection, you mean like bijection function? such as
Yeah, exactly.
Like,
This is exactly the same thing. Yeah.
so 1-to-1 and what was
Onto.
onto, yeah, those two.
So we hit all the value inside of Rn. So just for computation purpose, this is equivalent to check that the matrix P0 is invertible.
So in this case, invertible means that if you were to multiply it by its inverse, you would get the identity matrix.
Yeah, so the matrix has an inverse matrix.
Okay.
And also one practical thing, if you want, so sometimes it's long, but you will see with my example, it will be relevant. One way you can check if the matrix is invertible if it's a n by n matrix. I mean, if it's not an n by n matrix, it's definitely not invertible.
Do they have to be symmetrical matrices?
No, they don't have to be symmetrical, but they have to be square matrices. Otherwise, they cannot be invertible. So they have the same number of row and column.
So, wait, then what's the difference between a square matrix and a symmetric matrices?
So symmetric matrices just mean that it's symmetric along the diagonal. So the matrix has to be equal to its transpose.
Oh, okay. And what does it mean when it's symmetric by the diagonal? Does that mean it's like basically like the same pattern along the diagonal, or is it like all ones?
So basically, if I wrote a symmetric matrix, 2x2 matrix, for example, you will get something like that.
Oh, okay.
So if you flip the matrix along the main diagonal, you get the same value in the upper part and the lower part.
Oh, okay.
So for example, a 2x2 matrix can only be of this form.
So if like A and B was like ones and then C and C are like zeros, right? If you flip it, it still remains the same.
Yeah.
Okay.
Or another way of saying that is a little bit more fancy, saying that A is equal to its transpose.
Oh, okay.
Because all you're doing when you're doing transpose is you're just flipping the row and the columns.
And this is symmetric matrices, right? Not square matrices.
Yeah.
Okay.
Yeah, no, square matrices is just a 2x2 matrix, so it doesn't have to be
It could be like 2x2, 3x3, as long as it like remains the same for both row and column.
Yeah.
Okay.
Okay, so what's the theorem say? It say, okay, if our differentiable at some point P0 is invertible, so what does the theorem say? It said that then if we shrink our domain, so for example, we looked at, I don't know, we'll write something like that, and we're also gonna consider some V inside of Rn. So I also restrain the codomain. So if we shrink, and also we want this to have the point P0, then this is a bijection. And the inverse function is also of regularity C1.
What do you mean by regularity?
So I mean, there's like kind of a question we have to ask is if a function is a bijection and differentiable, will its inverse function also be differentiable?
Is that what regularity means?
Yeah. So here it means, here by regularity just means that the inverse function will also have all its partial derivative continuous.
Oh, okay. So basically it's just saying like is the inverse function basically as differentiable as like its actual original function, right?
Yeah. You can find that, for example, if f is of class C2, so all the second derivative are continuous as well.
You mean that there are, so like with that in mind, you mean there are examples where like say if you have an original function that's differentiable, but then if you take its inverse it's not differentiable? Exactly,
there's an example. You want me to show one? It's really quick.
Yeah, you could show one.
Okay, this is actually a very good example because it's a one-dimensional example.
Okay.
let's look at this function.
All right.
F of x equals x cubed.
Mm-hmm.
So its inverse function would be
the cube root.
Yeah, of x.
Oh yeah.
And what you can see if you compute the derivative of that guy at 0, you find this, right?
Right.
And what you find is if you evaluate to 0, you find 0, right?
Mm-hmm.
And what's going on is if you look at square root of the cube root of x,
right?
This function is differentiable, but not at 0, right?
Mm-hmm. Yeah, it's not.
You get like, and the reason why is because this guy has like a 0 slope, right?
Mm-hmm.
And when you look at the inverse function, you will get like some like infinite slope at 0.
Okay.
So to speak.
Yeah.
Yeah. So this guy is not. And the condition in the theorem of inverse function theorem of checking if the differentiable is invertible.
Yeah.
In the one-dimensional case, it's just equivalent to check that the derivative at that point is not 0.
Okay.
So here you see the problem is we found that the derivative at 0 is 0. That's the reason why f the inverse is not differentiable at that.
Okay.
Okay. And now I'm gonna give you a nice application of. So we're gonna do a computation.
Mm-hmm.
We're gonna do polar coordinates.
Okay.
Okay, so we want to be able to express vector inside of R2 as the radius and the angle, right?
Mm-hmm.
So let me just define the map that go from polar coordinate to R2. So it would be something like that. Okay, here I have to be careful about my angle. So this guy will be 0 plus infinity. So you can think that of the radius.
And it's an open interval, right?
Yeah. Times. So what's the angle we should put? Maybe 0 to 2 pi.
Yeah.
The reason why I have to put those hypotheses is because if I let, for example, 0 to 2 pi to be inside of my interval, I will get into trouble because I will have like 2 theta that represent the same point inside of R2. That's why I have to do some.
So from 0 to 2 pi, that's the x, and from 0 to positive infinity, that's your angle, right? That's the theta.
Yeah. So yeah, think of that as your radius and think of that as your theta. And we're gonna map to R2. But of course we're gonna miss some points. So maybe what point are we gonna miss? We're gonna miss the point there are the forms like that. So maybe I can just draw a picture. So we have a plane here that goes from 0 to 2 pi, excluding the 0 in 2 pi. And here you have 0 to, you just have the real line. Actually, I don't want to have those boundary. I think it's a bit annoying. So I will just change it to be minus pi to pi.
Okay.
There's like kind of a few angles you can choose to define your polar coordinates. So okay, maybe I will just write everything down. So here what you get is you get some pieces of a plane, right? So let's maybe call those axes. So I get 2 axes in this plane. The x direction, this part is my radius, and the what we'll usually call y is not the theta. Is not the theta. Okay. And this is defined, as I said, to so R just to be positive, and this guy has to be between minus pi and pi. Yeah. And so what phi does is it map this guy to the regular R2 with the usual coordinates, right? And if we want to spit it out all the, I mean, I'm sure you've seen that many times, but if we want to write this map explicitly, we will write something like that.
Right, the polar coordinates.
Polar coordinates. And so if it's a change of, okay, so when you have coordinates, okay,
yeah,
you want it to be invertible, right? Because you should be able, I mean, just logically to be able to change coordinates, right?
Right.
So I mean, it has to be, for example, I mean, you want to be invertible in this domain because, for example, if you map 2 points to the same point, in, for example, in R2, you get a little bit into trouble, right? It's not really a good coordinate because now you have like 2 points that represent the same point in your geometric object or whatever. So, I mean, this map, I mean, the restriction I put here a little bit careful is because I wanted this map to be 1-to-1. Or if you want injective, 1-to-1. Actually, in that case, it's even a bit better. It's even on 2, right? So just to be sure, we talk the same thing. Here I have the real line, and I remove the x-axis. Just to oh wait, no, not this side, not this part of the x-axis, the other part. This part I remove. I mean, the vector whose angle would be something like pi minus pi or pi, right? I remove that because I have ambiguity in the polar coordinates if I use those. Okay. And now what I want to show is I want to show that this is also differentiable. So its inverse is differentiable. So we're gonna do that, okay? And usually what you could do is you can, I mean, there's like sometimes you do that in textbook, but it's a little bit annoying. I mean, it's a good time to try to do it at least once in your life.
Is this related to what we were explaining earlier about the inverse function theorem?
Yeah, we're gonna use it.
Okay.
So one way to do it, which is a little bit painful, is trying to write the r and the theta in terms of x and y. Okay.
The r would probably be the square root of x squared plus y squared, and
exactly. And theta you have to worry a little bit because I mean it would be something like tangent of y over x or something like that, and you probably have to have a little bit fuzz about the point be antipolar and stuff like that. So it's a little bit messy.
Yeah.
But it's a good thing to do once in your life, but just once.
Just once in your life.
So what I'm gonna do is I'm gonna treat the first I mean that's really a thing we do when we do computation. We treat the first coordinate as if it were a function of r and theta. Okay. And I want to show that the inverse is differentiable. So as I said, we could do like the manual labor of just finding an inverse, as you said, we can do it. In the case of polar coordinate, we can actually do it explicitly, but in general case, we cannot. Because it will be like too hard to do it. So here I'm gonna give you like a method that works like a very general method.
Okay.
So what we're gonna do is we're gonna try to apply the inverse function theorem. Okay. So what we're gonna do is we're gonna take a basis for our plane in polar coordinates. So ER will just be 1, 0, and E theta will be 0, 1. Okay. And we're gonna do the same for the XY plane, okay?
Okay.
So those, just to be sure, those are bases for vector space, right?
Mm-hmm.
I mean, polar coordinates is just a map from a plane to a plane, the map is defined like that. But at the end of the day, we're just mapping a plane to a plane, and we can take a basis of the vector space.
Mm-hmm.
And so what will it get? So the reason why I took those bases is because now I can compute the Jacobian.
Okay.
Okay, so maybe we can say I'm computing the Jacobian at points r theta instead of a domain.
Mm-hmm.
So what will it be?
So like so basically we're differentiating r and theta, right?
So we're differentiating with respect to r and theta, yeah.
Okay.
So maybe I can just spit it out a little bit more. So what is a polar coordinate map doing? So what we're doing is we're writing the first component as a function of r and theta, and we're writing the second component as a function of r and theta as well.
Mm-hmm.
And what I said before, if you remember, the first column will be the variation, for example, in the r direction.
R direction, yeah. So we would have to differentiate with r, which basically is just 1 in this case. So that means it would probably be like for the x, it would be like cosine, and then for the y, it would be like sine.
Exactly. So I'm just gonna write it everything, but you're absolutely right.
Yeah. Hey Famish, I just saw you. I saw your message like a while ago.
And for the other column, you will get the same thing, but for oops,
yeah.
This is supposed to be a R.
Yeah, I think I've seen this in a book too. Like I think one matrices, it's like one of the signs is negative, right? It could be on either the bottom or the top one, right? So it's going to be like cosine, the diagonal would be cosine, cosine, and the other diagonal would be like sine and negative sine. Right?
Yeah. So if we do the computation, as you said, we will get cosine of theta, sine of theta, minus r sine of theta, or cos theta. So, as we know that pi is a bijection, we can. So we only need. So at the end of the day, we want to show that the inverse of phi is a differentiable function, right?
Right.
So we all do is a bijection. So it map points. I mean, it's a bijection between the points. But we want the inverse map to be also differentiable. And as I said before, so we can use the very intensive labor of the inversing the function, but here we can use the inverse function theorem. So as phi is a bijection, we only need to check. Oops. Check that the Jacobian of r theta is invertible at every r theta.
Okay.
So the reason why we only need to check that is because of the inverse function theorem. So here it's a bit annoying to show that this method is invertible. I mean you probably learn a few ways in linear algebra. You can use Gauss-Jordan and stuff like that. Here probably the easiest way is probably to compute the determinant. So we're gonna do that. So determinant of this to the point r theta. So what would it be? So we will have cosine times arc times cosine, so we get r times cosine square. And on the antigonal, we're gonna have plus r times sine squared theta.
So why are you doing the determinant again?
Because there is like a very powerful theorem in linear algebra that if a matrix determinant is not 0, then it's invertible.
Oh, okay.
So if I compute the determinant of this of my Jacobian and I found it's never 0 for every r and theta, I know that the Jacobian is always invertible.
Okay.
So here what I found, so obviously I have the identity cosine theta squared plus sine squared.
Yeah, you just factor out.
Squared is 1.
You factor out r, and basically that just equals 1, and then basically you're just left with r.
Yeah, and this is never 0 because we assumed, at the beginning, that r was in that interval, right?
Yeah.
Otherwise, if I don't have this condition, polar coordinate will not even be a coordinates, right? Because the point at the origin will be mapped by there's a lot of points that could be mapped to 0, right? I can just put the r equals 0 in theta to be whatever, and it will always map to 0. So the conclusion is Feynman is differentiable.
Okay.
You can even say more actually, but I don't really want to do it because
it's fine.
Actually, what you can show is that so if x is r times cos theta and y is r times sine theta, then you can show actually that the differential of oops, I should write it able to see. I'm sorry.
It's alright. And by the way, how's it going, Zach? Welcome. Yeah, we're doing the inverse function theorem.
So what you get here is that if you take a differentiable, so we just check that this linear map is invertible by checking that the matrix is invertible, right? So it has an inverse, and the inverse is really easy to compute. It will just be this guy. So the differential of the inverse of the function.
Okay.
So in other words, if we want to go back to the language of matrices, what it means is that if you want to compute the Jacobian of the inverse function, you just need to inverse this function. This matrices, I'm sorry.
Which matrices?
The one I just put an arrow.
Oh, okay.
So the Jacobian of phi.
Oh, okay.
So this is like a very ND computation because you cannot compute. Usually it's hard to compute the inverse of a function, but it's not hard to compute the inverse of the. It's not hard to compute the. It's differentiable because it's just the inverse of the Jacobian, and inverting a matrix is not something too hard to do. For example, you can use a Cramer rule to have explicit formula for all the coefficients if you want.
Like one of the, I guess, like the computational methods of trying to get the inverse of matrices, right? It's basically you kind of like do what is it called? What type of elimination is it? It's where you basically try to turn everything into an identity matrix, but then
yeah. So this is like elimination with like an augmented matrix.
Yeah.
But you can also use Cramer rule. There's like a few methods that you can use.
Gauss-Jordan elimination. Yes, thank you, Zach. That kind of thing. Yeah. Because like I remember like in linear algebra, like if you have a matrix here, but then you have the identity matrix here, and you kind of like put them together and you try to make the one side opposite of the other. So you turn one side into the identity matrix and the other side, you end up getting the inverse for free in that particular instance.
Okay.
Go on.
Okay, now I just want to stretch a little bit of something that's important. It's not usually explained in beginners book, but I want to. I think it's important, so we'll just explain it.
He's putting me through the ringer, guys. He's putting me through the ringer.
So let's say I.
Oh no! I was gonna say you're gonna make my brain explode, in a good way.
So let's say you have some. Okay, by the way, I just want to point out something.
Yeah.
You know the psi we wrote?
Which part?
What?
Which part did you?
I'm sorry, the phi at the top. The map that map
Here it is. Yeah, I see.
our theta plane to the xy plane.
Right.
One way to think about it, it's actually a coordinate change function.
So I'm guessing like phi in this case is like the I guess the transformation matrix that transforms like this coordinate system to the other one, right?
Yeah. So it maps polar coordinates to Cartesian coordinate.
Okay.
And I just want to point out something. So if we have, for example, a coordinate change like that.
Mm-hmm.
There's actually a few conditions you want to have on this map.
Okay, such as?
Okay, first of all, if you want to compare coordinates, you want this to be a bijection.
Does it always have to be a bijection?
Yeah, I mean, if you want to compare points, yes, it has to be.
Oh, okay.
But for example, if we go back to our example, you know, example, Cartesian coordinates are defined everywhere on R2, right?
Mm-hmm.
And here to get a coordinate change map, what we did is we shrink our domain, right?
You're right.
We get rid of like the minus the x axis, like the negative part of the x axis, to get bijection.
Okay.
So you can do that in general when you want to do coordinate change. You might have to shrink a little bit your domain, but you can do a coordinate change like that.
Yeah, like.
And this map should. Right.
Like before you continue, right? The one question I think I think like many of us that learn like algebra like have is, it might not be related or anything, but what is the difference between a codomain and an image? Because those two I sometimes get mixed up with.
So usually the image will just be like all the points are mapped inside of Rn.
Uh-huh.
For example, if a map is phi like that, we can look like at all the. For example, we have a map from U to V. We can look at all the points that go from U to V.
Mm-hmm.
Okay, so maybe we will not hit all the points in V, but it will be some subset, right?
Is that basically like of only the function, like basically all the let's say like x and y, right? The y is basically the output. Does that mean that the image is basically like all the y coordinates that the function is capable of reaching?
Yeah. All y that the function can reach.
So so is that similar to like, because I think there's another word they use like in elementary school, they use range, like to define. Are those two like equivalent, or they're different in some ways?
I mean, range usually is usually used for domain, but
yeah, because like so like what is the codomain in that point? Because they seem like similar in that case.
So the codomain is basically in what space are you mapping to. Maybe you will not hit all the points. That's like the difference between the codomain and the image. In the image, you hit all the points in the image, but in the codomain, you don't necessarily hit them.
So, is the codomain mainly related to space, while the image is mainly related towards, like, I guess, the function itself?
Yeah. So the codomain is kind of like an ambient thing, if you want.
Oh, okay.
But so, all those things are relative, right? If you shrink like your codomain, then it can become your image.
Oh, okay. So basically, the codomain is related to the space that you're in the output, whilst the image is basically just everything that the output can reach. But
so it would be like a subset of that.
But it doesn't take into account like the space that it's doing it in, right?
Yeah.
Okay, I get you now. All right, yeah. Go on, sorry.
So we probably want a few conditions on that map. So if you were a topologist, you will probably ask this map is, they will ask it to be continuous, but they want a little bit more. They want also the inverse to be continuous. Okay. So continuous is probably a good one. I mean, and probably the inverse, you also want it to be continuous. But here, for example, in physics or in differential geometry, we want a little bit more.
Okay.
We want to be able to map direction.
All right.
Like we would like to, in certain, what I mean is we would like to also be able to map direction in the sense of vectors.
So does that mean you would actually have to have a metric in this, case?
No. Just what it means that this map has to be differentiable.
Oh, okay. Okay. I don't know if I used the word metric correctly in that case.
Actually, I will show you a construction with the metric at the end. That was what I was planning to do. So you will have an example of a tensor, which is a bit cool.
Yeah, but we're pretty short on time, so we'll probably do that like the next time if you're able to.
Yeah. Okay, maybe I can just do it right now instead of.
If it's short, yeah, you can do it. Yeah.
Okay. So in R2, with the Cartesian coordinate.
Okay.
We have a metric. I mean, here metric is kind of it's kind of a fancy word because it's really just a scalar product.
And maybe we should probably explain what a metric is, just in case if anyone's listening in that doesn't know what a metric is.
Well, I don't really want to get into metric because if I want to get to metric, I have to talk about the formal definition of a tensor, and I have to talk about the.
Oh right, yeah, that's right. Yeah.
I just want you to have like an example of stuff you can do.
That's fine. That's fine. Yeah.
So what is it? So if you have a vector, I don't know, represented as v1 ex plus v2 ey, and you have like w, which is the same thing, but let's say with w1 and w2 as component. Okay, so ex and ey are the standard basis. Yeah.
Standard basis. Right.
So the metric will be something like that. So what you do is you just multiply v1 with its corresponding coordinates, so w1 plus v2 times w2. Okay, and this operation takes vector inside of R2 and produces you a scalar, and it verifies a number of properties that we will not get into, but
yeah, right, yeah.
And now I want to consider. So, what I would like to describe is what does this metric looks like in polar coordinates.
Okay.
And first of all, I have to explain a construction from linear algebra, okay? So let's say I have a linear map from Rn to Rn with a scalar product on Rn. Okay, maybe I will just put a little bit, so maybe I will put a 0 and a 1 ici just to differentiate the two space. So what I want a scalar product on this guy. Okay, so this guy has a scalar product.
Okay.
And now I want to steal it. I mean, mathematicians are really good to sometimes steal stuff. I want to steal the scalar product that I live here and put it on this space. Okay. And one way you would do that is, so maybe I don't know the scalar product, we can call it G as before. What you will do is so usually you have a very fancy notation. We call it F with a little star on it, and we put what we steal.
What does the star represent?
So it's supposed to be called the pullback.
The pullback.
Yeah.
Okay.
So the idea is we have some structure that live on this space, and we want to pull back to that guy.
Like when you say pull back, does that mean like we want to be able to go back to the original? Like I mean,
yeah,
we want space. Yeah,
we want to go back to the first space.
Okay.
I mean, I prefer my analogy. You just want to steal. You just want to steal the stuff on this space.
Oh, like how about this? It's like you're basically a person that's observing someone do something, but you're measuring it in your own coordinate space. whilst like the other person, they're trying to measure you from their coordinate space, but you want to stay in your own space by
basically that's what the example will get into, because what we're gonna do is we're gonna steal the metric from the Cartesian coordinate. So now we have a metric in the polar coordinates, and now we will be able to compute distance and all the thing we want to do with the metrics in our in our polar coordinates.
Okay.
So it will be handy stuff to do.
All right.
And if you do it in linear algebra, what you will do is you will ask. So if I have two vectors that live inside of this first space, what I can do is I can just use the metric on the other space and just push my vector along F. Okay, and here I'm kind of forgetting a condition. We need this map to be injective. If you to be invertible. The reason why you want it to be invertible is because usually when you have a metric, you want it to
be differentiable at both ways.
Well, not that. This is just like a linear algebra condition. We don't have differentiability yet, but what you will get is that if I give you a vector and you compute like its norm, so you just take the metric and you just evaluate GVV, you know, if you want to get the length of your vector V.
Oh, okay.
I mean, it will give you the norm square, but I mean the same thing. If V is non-zero, you would like it to be non-zero, right?
Right.
A vector which is not zero should have a positive length. But the thing is, if this map is not invertible, what's gonna happen is some vector will be mapped to zero. Some non-zero vector will be mapped to zero.
Oh, okay.
And what's gonna happen because of this definition? Well, if, for example, V is mapped to zero, then a scalar product with himself will be zero, because we just basically compute the scalar variable. So we have to be careful, and that's to be invertible. Okay, now I want to go to our example to see what we want to do. So what I'm gonna do is I'm gonna steal the metric from Cartesian coordinates to polar coordinates.
Okay.
And if you look at what I have here I have a linear map.
Okay.
Okay, but the thing is, my phi itself is not a linear map, right? Like phi is very non-linear, right? You do some weird thing. For example, it maps like a line to a circle, stuff like that. So it's really not linear. But I have one thing that's linear. I know that if I fix some r data points, I get a map from R2 to R2, which is linear, right? The differentiable is linear.
Okay.
And what I'm gonna do is I'm gonna steal the metric with that guy.
All right.
So okay, so just to be sure, so what we compute previously. I mean, this is the Jacobian the matrix we wrote before, but I just write in this another format. So if I push the vector, the standard basis for the r theta plane, so for example, this is just 1, 0. What we computed previously, that it would be basically computing the derivative along the partial derivative of r for all the coordinates, right? So we will get something like dx, dr, ex plus dy, dr. So those guys are just the first column in our Jacobian matrix that we computed previously.
Okay.
And we already know what are those. So those are cosine e of x and sine of e of y, and we can do the same thing for theta as well. So what was it for theta? It was like minus r sine?
Yes, I believe. Let me take a look.
And the other guy is supposed to be r cosine ey.
Yeah, r cosine.
Okay. So what we did, we just compute. I mean, this is basically what we get in the Jacobian. So like
Mm-hmm.
This guy is just the first column, and this guy the second column.
Mm-hmm.
So let's compute our metric on that. So let me call it.
And EX and EY are supposed to be the partial derivatives, right?
And so the EX and the EY are just like a basis for R2.
Oh, basis over there.
Right. Okay, the thing you said about partial derivatives is right,
Mm-hmm.
but we kind of need another definition of the derivative to do that. That's like the differential geometry definition.
Mm-hmm.
So those guys could be replaced by partial derivative.
Oh.
But I will not get into that because I need to talk about first order linear operator and stuff like that.
Right.
Here I just want you to imagine that EX and EY are a direction.
Okay.
So let's go back to our initial plane of stealing the metric.
Mm-hmm.
So this guy by definition would be J evaluate to R theta.
Mm-hmm.
Yeah, I want to do this computation. And maybe you can help me a little bit.
Okay.
So what would be this guy? So basically what we're gonna do is we're gonna multiply. So basically what we're gonna do is gonna square each coordinate, right?
Mm-hmm.
Because this is a standard metric, yeah.
Yeah, so like wait, square every part of the expression?
No, just like the coefficient here.
Okay, so yeah, if you square those, then basically, oh no, this is a EY and EX, so we can't factor those out.
No, there is no EX EY. Because okay, maybe I can go back to the definition of the usual metric. So
Mm-hmm.
I think I wrote something like that. So
Yeah.
the usual metric of that is you do U1 times W1 plus U2 times W2, where U is U1 times E1 plus U2 times E2, and W is the same thing but for W1 and E1 and so on. So we just express U and W in the standard coordinates.
Oh, okay.
Standard basis, I'm sorry. So what we did here in the computation above is we exactly did that.
Mm-hmm.
We push the ER along the differential, and we have its expression in the EX and EY basis, right?
Right.
So, I mean, if I want to compute the length of a vector in the standard metric, I just take those two coefficients square, right? Just Pythagoras theorem. So here I just get 1.
Okay.
Okay.
Mm-hmm.
Okay, I don't really want to do the... Maybe that's an exercise you can do, but you can check using like the expression, just unravel everything, that ER E theta is 0.
Okay.
So they are orthogonal. And probably the only important thing that is interesting in that computation is what happened to E theta.
Mm-hmm.
So what are we pushing? We're pushing EF R theta, E theta. Okay, so what would be the thing we get here? So we'll get sine minus r sine square plus r cos theta square. So we'll just get r2. And now we're done.
Okay.
So what we did is, I mean, okay, this is like maybe a thing, if you're not familiar with scalar product, you probably don't know, but pretty much like linear transformation, if you know what happened to a basis, you know everything.
Okay.
For scalar product, it's the same idea. If you know what's the value of the scalar product on all the elements of the basis, you know everything about the scalar product.
Okay.
And so what we get in general, so if we have, for example, v, which is a vector in the ER theta plane, so maybe I can write it, like something like that. So VR plus v theta, e theta, and we do the same thing for W. So what we just compute is that if we want to compute the scalar product of those two guys, using the metric that we stole, we will pretty much get the usual Pythagoras theorem. The only difference is we're gonna get some correction terms on the theta part.
Oh, okay.
So we're gonna get VR. I mean, we pretty much get the standard metric, except we get. So this is like standard. But what we get is on the theta part of our expression, we get some r squared appearing.
Okay.
This would be v theta and w theta. Okay, maybe I should be a little bit more precise. Here is for the point r theta. And here you have something which is a bit weird if you think about it.
Okay. Alright.
We did not really steal a scalar product, right?
No.
As we play. We steal a family of scalar product. Because if we look at our expression here, this expression depends on r. So depending on which point on the plane r theta you steal the metric, the metric will change.
Okay.
Okay. I mean that's kind of a natural thing to do because for theta, because if you imagine in the polar coordinate, if you go like for vector which have a big R, right? The circle given by like r to be constant will be like very big, right?
Right.
So if you do some little movement along the theta directions, if you change a little bit the angle, you're gonna change the length by a lot, right?
Yeah.
So that's why we get the r square terms appearing here.
So the r square in this case is sort of like the scalar that kind of adjusts for the change that theta is going to create for r in that case.
Yeah. Okay. Yeah. So if, for example, okay, maybe I can write the plane here. So we have r ici and we have theta here. So the drawing is not bad.
Yeah.
And it's good. So what's gonna happen? Okay, if for example for this r we look at a small variation in theta, and for a bigger r we look at a variation of theta. So what you will get in the Cartesian plane is you will get my drawing is not good, but
that's okay.
you will get like a small circle for like the first one, and you will get a bigger circle for the second, right?
Right. Because the angle makes a difference on like how big the circle will be.
And if you like do like for example, if you look at the variation along ER, E theta, I'm sorry, like along the angle.
Yeah. If
you're on a smaller circle, the vector you will get will be much smaller, versus if you're on a bigger circle. So this is like one way you can make sense of that.
Okay.
And I mean, yeah. So this guy change.
I mean, if you think of like what is it, like the centripetal force, you would probably think of the r in this case as sort of like the velocity. Like
the theta would be the the theta would be the thing. So I mean, we kind of failed at some point. I mean, we kind of failed, but not really. Like, in general, if you have coordinate and you try, for example, to pull back a metric like we just did, we don't get a single. Like, we don't get, for example, if we have a scalar product on the Cartesian coordinate and we pull back to our coordinate, we don't get usually a scalar product. Instead, we get a scalar product for every point r theta.
Okay.
And here this is clear because we have our scalar product depends on the r point that we like. Depend on the radius of where we were.
Well, yeah, because like the coordinates and polar coordinates, they have to rely on both the independent variables on each other.
Yeah. And I mean, this is like a very good example because what you just did. I mean, I don't know if you realize what we just did.
Yeah, go on.
So this guy here, having a family of scalar product that depends on r and theta. This is an example of a Riemannian metric.
Okay.
And you see the thing we did? We took a scalar product and we put it back to our space.
What is it that you want me to be looking at now?
Like this thing we compute.
Yeah.
Like the stealing part we did. We took something that was in the Cartesian plane and we put it back to the polar coordinate. Yeah. This is a contravariant change of coordinates.
Okay.
So I mean, we're probably gonna develop it a little bit better next time, but yeah. Basically, Riemannian matrix are a thing called 0-2 tensor. So what it means is it takes two vectors and spit you a number.
Okay. Right.
I mean, usually they are called bilinear form, which some like nicer properties. And if you have a linear map in linear algebra, if you have a bilinear map, you cannot usually push bilinear map, but you can steal it like we did. We can pull it back.
Yeah. Because I think I heard I think I read it in the book the book I'm reading. If you guys want to know what book that is a student's guide to vectors and tensors by I think his name is Daniel Fletch. I think that's his name. Basically, they said the book. He basically says that covariant vector components they go with the coordinate system. Whilst like quadravariant basically goes against the coordinate system.
Yeah. So this operation of stealing stuff, like if we go back to the thing I wrote in the top here, like I don't know if you can follow me.
Let's see. Oh yeah, here.
Yeah, this part, this is like a very like contravariant thing to do.
Okay.
This is like the prototype thing you have to do, like.
So the reason why covariant vector components are important, or at least in this case, is because like I guess in relativity, like space-time is curved. So basically, the vectors will always go with the coordinate system that it's on, right? So that's why you need covariant vectors, right? In this case?
So usually what you want to do in relativity, for example, study a vector field or stuff like that. Which is like things that you can push along the derivative if you want, sort of thing. You can push it along it. But you still have covariant vector field, or they also call one form. And those are contravariant, so you have to you cannot push. You can only pull it back.
Right.
And pretty much
because the space or the coordinate system dictates how the vector is like convex or like lengthened in that case.
Yeah, so usually in relativity, what we care is pretty much the geometric picture. So you care about the metrics. This is very like the star of the show in relativity. So you want to be able to pull back metric. For example, if you change coordinate, you want to see what happened. I mean, what we did, the computation we just did is exactly what you will usually do when you want to compute what your metric looks in other coordinates.
Okay, so I guess like to end your lesson, Sascha. The important things we should take note of in summary wise, like I guess like in a list, we should concentrate on for the relation between linear algebra and multivariable calculus, right?
Yeah.
What are the three key things we should take away from today's stream that you were trying to show us?
So basically, a lot of construction in differential geometry and relativity is construction from linear algebra.
Okay.
For for example, I mean, you just saw a very good example. For example, the example of stealing a scalar product, or the idea of pullback. In different geometry, you just represent, for example, if you have a Riemannian metric, you just represent chains of coordinates, like just writing down your Riemannian metric. And there's like a correspondence between scalar product and Riemannian metric in some sense. Scalar product is like the local theory, and the Riemannian metric or the global theory. And pretty much in all concepts from linear algebra almost can be like, there's like an analog in differential geometry.
Okay, I see.
So usually a good thing you have to think is, for example, if you want to approach tensor, you better start with looking at the linear algebra.
Okay.
And when you do the linear algebra, then you can apply it to differential geometry like we did. And the key point to be able to do that is using the differential, right? Because I hope I was able to convey this idea during the stream, but what is so special about differential function is they have their differential, right? And this map is linear, so you can do all your linear algebra tricks like theory. You can apply it to this map.
Oh, okay.
And then this is like where most of the differential geometry theory come from. I mean, at least the basic part. After that, there's like some topology, but I mean, all the thing about metrics, curvature, and all the stuff is all come from this idea.
Yeah, I think what Sascha's main point was is that, like, if you want to know the complex, I guess the complexities within coordinate systems, such as like general relativity, or maybe even quantum mechanics, because quantum mechanics also involves linear algebra too. Start studying linear algebra, and then like if you're also learning multivariable calculus, see the relationship between the two. And I think the relationship will actually allow you to think about things more complicated, like, you know, a curved space-time, or maybe maybe a field that's like vibrating constantly, and you're just trying to figure out how does a vector like basically go with that field, instead of like the vector just being on top of the field or something like that, like, because vectors don't change.
Yeah.
Okay.
And usually I think it's a very good approach. I mean, I like the mathematician Pierre Deligne, which is like a very famous mathematician. And usually when you do a lecture, you usually start, okay, let's start with the linear algebra, and then you explain stuff in linear algebra. Usually it's simple because people are very used to linear algebra, at least when they're a mathematician.
Yeah.
And then what is cool is you will usually talk about a very like hard topic.
Yeah.
And you will define some definition, but if you've seen the linear algebra picture, which is very clear, you just see that the harder part, like when you go to the harder theory, is just an application of linear algebra, but in a more complicated context.
Yeah, because like I think when I started learning linear algebra, I think the subjects that stuck with me were the operations with matrices, and I think mainly the vector operations. But then when it came to things like vector spaces and basis vectors and eigenvalues and eigenvectors, I think those are the things that I struggle with most, because I am like, how do I best solidify those facts in my head with something that I can actually visualize and actually implement with questions that I can use them to solve questions that I have about, like, you know, whether it be physics or whether it be like something like within, like, I guess a computer system or something like that, or something physical. That's what I mean.
Okay. I would like to end the stream with one note.
Yeah.
So we did a lot of theory, and maybe some part of it you like got over your head because, you know, it's hard to follow, but during 2 hours. So I would like to propose some exercise for you to work maybe next time or in your free time. But I think those exercises would be great.
Okay. Luckily, I have a notebook in front of me, so I can write this down.
So I would like you first to review the metric computation in polar coordinates.
What do you mean by computation?
Like the way we were able to express the metric in terms of ER and E theta.
Oh, okay. So like so basically the metric of polar coordinates, right?
Yeah.
Is that to the Cartesian coordinate system? Like from polar to Cartesian? Okay.
Yeah. So I want you to review that. Okay.
Okay.
So this
okay.
is like more like a breezer just to. I mean, because I probably went too fast on some stuff and maybe.
Yeah, I'll make a note to play with it too, like so
Yeah.
that way I can have a better idea of like how it works.
Yeah. In some sense, I kind of gave you the solution. I like wrote almost everything out.
Mm-hmm.
And I want you to think. If you have questions, don't. You. I mean, you can just ask me, and I will be happy to answer.
Oh yeah. I'll try my best to like think through it, and if I get really stuck, I'll ask you.
Okay, and then so I mean, we did for Cartesian to review the metric for coordinates. Sorry.
And that's from polar to Cartesian, right?
Well, I don't want to do that because you will just get back the usual metric. What I want you to do is do it with the other coordinate system.
Okay.
Do the same exercise for, I mean, for this case, it will not be for R2 because there is not many interesting coordinates, but let's say for spherical coordinates,
Mm-hmm.
what else do we have? Cylindrical.
And that's the metrics, right?
Yeah. So again, you will have like a change of coordinate. There will be some map that go from. I mean, I don't want to write everything, but it will be some subset of R3 to R3.
Mm-hmm.
That map that give you example spherical coordinate to Cartesian coordinate, and in that plane you will have like two axes. You will have the R phi and you will have the psi.
Mm-hmm.
R theta phi. I'm sorry. And I want you to express the metric in terms of the standard vector. So 1, 0, 0, 0, 1, 0, and stuff like that.
So these are so wait, it's like ER is equal to 100 or 101?
1, 0, 0.
Oh, okay.
Sorry.
Sorry.
So just the standard basis in the R theta.
So like if I'm gonna reinstate these questions, so what you want me, and if you guys in chat want to engage in this exercise, you're more than happy to do so. So basically, the first exercise is to basically just review the metric computation of polar coordinates to Cartesian coordinates.
Yeah.
Then the second exercise is basically do the same thing, but I'm guessing basically is it from polar coordinates to spherical coordinates, and then from polar coordinates to cylindrical coordinates, or is it a different coordinate system in general, like Cartesian?
So we're gonna do spherical to Cartesian and cylindrical to Cartesian, just like we
okay.
did.
So two Cartesian, okay.
Like I mean, exactly the same setup we had before for polar.
Okay. All right. So like what you did with the phi, right? From R3 to R3. What is that supposed to indicate for us? Is that like a hint to something?
Well, basically what you get is you will get. I mean, so you will get a metric on R3, but R3 has like. I mean, when you look at it in spherical coordinates, there's like 3 coordinates.
Mm-hmm.
So you have one axis for the R, one axis for the theta, and one axis for the phi.
Okay.
And what I want is the metric in terms of those guys.
Oh, okay.
If we go back to the thing I wrote before, this is pretty much this computation.
Which one?
The one I just put blue marker.
Oh, okay.
Here. This is pretty much this step. So it pretty much involves computing the Jacobians. That's like the main thing to do. And after that, compute scalar product.
Okay. All right.
So I think after that you will be.
All right. So for these exercises, Sascha, what is it? So we should just only, I guess, practice our linear algebra with these problems, right?
Yeah.
Okay, so linear algebra. Are there particular sections of linear algebra that we should focus on to get us a better idea of how to solve these problems?
No, we just need to worry about the pullback thing I wrote at the top, like the formula.
Which formula is that?
I can't remember. I will put
okay.
star.
Okay. Just have to write that down here. And F star is supposed to be like
It's just a notation thing, so it just means we. So this is just like a name for the new thing we still.
Okay. All right. So I guess that's basically our assignment, our awesome lecture by Sascha. So thank you, Sascha, for like educating us on everything that's here. And you know, it's always an open door. Like if you ever want to give us another like awesome lecture on stuff that's very interesting like this, you're more than happy to do so. You just let me know.
Yeah. Hopefully you will be able to carry those computers.
Oh yeah, this is something I'm gonna play with in the weekend, definitely.
Yeah, I think that's something that's gonna interest you because really, when you understand those, you really, understand how coordinate change work in general.
Okay, yeah, you're giving me proper direction actually. Is there anything you would like to say to our global audience before we depart?
Drop a follow to Matt Spellbook.
Thank you very much. And also, guys, like if you're watching this on YouTube, thank you for joining us, like whether it be YouTube or Twitch. If you found Sascha's if you want Sascha to actually come back and give us another lecture, like put it in the comments down below if you're watching this on YouTube. And yeah, so I will post in the chat my YouTube channel, and also anyone from both platforms, whether it be YouTube or Twitch, you can follow us on Discord. And maybe oh yes, and if anyone's still in the chat, if you guys want me to do more problems because you just want to see if I can solve them or anything, you're more than happy to provide your own problems, you know, just have a little fun. Maybe it'll also help you learn the thing that you're trying to learn, because if you make a problem, maybe it'll help your brain like actually make the connections that you never thought of before. So first I will post up the Discord so you guys can access the Discord, and for my Twitch viewers, you can go to my YouTube channel and drop a sub if you like. Alright, so I think that will be it for today. So Sascha, thank you very much, and you take care and have a good rest of your day, my friend.
Same for you.
Alright, so I will log off of Discord, so I will see you like probably tomorrow for my next stream if you're going to be in chat.
Oh yeah.
Alright, so take care, Sascha.
See ya.
Okay guys, so we parted with Sascha, so I will say this to you guys to end the day. Always remember, everyone is precious. You guys are just as precious as everyone else, and I will see you guys tomorrow for another lesson on the Math Spellbook channel. So take care, guys. Bye-bye.